In this video, I'll explain the proof of Theorem 3 for the paper Uniqueness of DRS as the two-operator resolvent-splitting and Impossibility of three-operator resolvent-splitting. Theorem 3 establishes the impossibility result promised in the second part of the title of the paper. Although I will explain every step thoroughly, I will assume that you, the viewer, are familiar with the proof of Theorem 1. This will allow me to quickly go through the definitions and the results that are analogous to what we have seen in Theorem 1. We define the problem class 3op-RD to be the collection of monotone inclusion problems of this form, where A, B, and C are maximal monotone operators on RD. A pair of functions t, s is a fixed point encoding for the problem class 3op-RD if we have this bidirectional implication. The forward direction states that if we have a fixed point of the fixed point mapping T, then the output of the solution mapping S is a solution to the monotone inclusion problem. The other direction states that if we have a solution to the monotone inclusion problem, then there exists a fixed point Z star such that the output of the solution mapping is that given solution X star. To formalize the notion of resolvent splitting without lifting, define the class of mappings G similar to how we define the class of mappings F. Let I be the identity mapping that takes in as input an operator, a vector, and outputs a vector. Specifically, the action of I is to ignore the operators A and B and simply output the input vector Z. Let J alpha 1 be the resolvent with respect to the first operator. Formally, J alpha 1 is defined as a mapping that takes in an operator, a vector, and outputs a vector. The action of J alpha 1 is to ignore the operators B and C and output the resolvent with respect to A. We define J beta 2 likewise as a resolvent evaluation with respect to the second operator. Define J gamma 3 likewise as the resolvent evaluation with respect to the third operator. Let G0 be the class of mappings that contains the identity mapping and the resolvent evaluations with respect to the first, second, and third operators. Recursively define Gi plus 1 as a class of mappings obtained by addition, composition, and scalar multiplication of mappings from the previous class Gi. Finally, define the class G as a union of all Gi's. Elements of G map an operator, and a vector to a vector. If a mapping R is a member of class G, and operators A, B, C are maximal monotone operators on RD, then R with the operators A, B, and C fixed is a mapping from RD to RD. We say T, S is a resolvent splitting without lifting for the problem class 3op-RD. If T, S is a fixed point encoding for the problem class 3op-RD, and T, S is a member of class G. Now we are ready to concisely state the theorem. The theorem states that there is no resolvent splitting without lifting for the problem class 3op-RD. Let me clarify what the theorem is saying. Let's assume the fixed point mapping T with operators A, B, and C is a mapping from RD to RD. The fact that it's a mapping from RD to RD corresponds to the assumption without lifting. Furthermore, assume that T and S are constructed with finitely many resolvents of operators A, B, and C. Under this notation, there are NA evaluations of the resolvent with respect to A, there are NB resolvent evaluations with respect to B, and there are NC resolvent evaluations with respect to C. The parameters alpha, beta, and gamma are allowed to be different. So alpha 1, alpha 2, up to alpha NA, they are allowed to be different. Beta 1, beta 2, beta NB, they are all allowed to be different. Gamma 1, gamma 2, gamma NC, they are all allowed to be different. Theorem states that T, S still fails to be a fixed point encoding. Let me further clarify. Another way to state Theorem 3 is to state that no element of the near ring G is a fixed point encoding for the problem class 3op-RD. Assume for contradiction that T, S is a resolvent splitting without lifting. In the first stage of the proof, we will set up the notation. Let N be the total number of resolvent evaluations required to compute T and S. The specific value of N depends on how you count. In other words, the specific value of N depends on whether you simplify things and whether some resolvent evaluations are counted redundantly. All that matters is that N is finite. Since T and S are members of class G, which elements are finitely constructed, there is a finite evaluation procedure for T, S. This evaluation procedure provides a sequential ordering to the resolvent evaluations. Using this ordering, we label the resolvents J1, J2 up to Jn. where each ji is a resolvent evaluation with respect to operator A, operator B, or operator C. We call Zi the point at which ji, the resolvent, is evaluated, and we call xi the output of this resolvent evaluation. In the process of evaluating t and s at any input z0, we get z0, z1x1, z2x2, and up to zn xn in this order. Since scalar multiplication and vector addition are the only operations allowed aside from resolvent evaluations, each zi is defined as a linear combination of all the previous information. Likewise, the output of the solution mapping can be expressed as a linear combination of the inputs and outputs to the resolvent evaluations. Without loss of generality, assume that the resolvents with respect to A, B, and C are all used at least once in the evaluation of t. If this is not the case, for example, if the resolvent with respect to A is never used, then we can define Zn plus 1 as 0 and evaluate the resolvent with respect to A at this 0 input. This is equivalent to evaluating the resolvent at the end and not using the output. Let's say that the resolvents with respect to A, B, and C are respectively evaluated NA, NB, and NC times. Since we have n evaluations total, we have NA plus NB plus NC equals n. Let A1, A2 up to ANA be distinct indices, and let alpha 1, alpha 2 up to alpha NA be positive parameters so that the resolvent evaluation number AL is the resolvent evaluation with respect to A with parameter alpha L. In other words, XA1, XA2 up to XANA are the outputs of the resolvents with respect to A. Likewise, define B1, B2 up to BNB and C1, C2 up to CNC to be distinct indices, and let beta 1, beta 2 up to beta NB, gamma 1, gamma 2 up to gamma NC be positive parameters, so that XB1 up to XBNB and XC1 up to XCNC are the outputs of the resolvent evaluations with respect to operator B and operator C respectively. We express the evaluation of the fixed point mapping T at input Z0 with a system of linear and nonlinear equalities. This first linear equality defines Z1. This second linear equality defines Z2. This third linear equality defines Z3. This linear equality defines Zn. And the final linear equality defines the output of the fixed point mapping T. To clarify, we call this a system of linear equalities because it's an equality and it's linear. We call these the output of the resolvent evaluations nonlinear equalities because these are equalities but the resolvents are nonlinear mappings. Using Gaussian elimination, we can eliminate these non-zeros and obtain a simpler equivalent system. To summarize our progress, we have set up the notation and we have shown that these linear and nonlinear equalities define the evaluation of the fixed point mapping T at any input Z0.
Let's take a moment to consider what happens with Douglas-Rachford splitting. This will help us understand the direction this proof is headed in. Under a similar formulation, DRS has these linear equalities and these nonlinear equalities. With DRS, we can combine these linear equalities with this fixed point condition to show that x1 is equal to x2 when the input Z0 is a fixed point. More specifically, we can add the fixed point condition to the linear system, left multiplied by this, to obtain this linear system, which is equivalent to x1 minus x2 is equal to 0. This is equivalent to combining this definition of the fixed point operator T and this fixed point condition to conclude that x1 is equal to x2 when the input Z0 is a fixed point. Remember, x1 and x2 are the points at which we evaluate A and B indirectly. Precisely speaking, we evaluate the resolvent with respect to A directly at Z1, and that gives us this monotone inclusion. Reorganizing the monotone inclusion gives us this as the output of the operator A at x1. Likewise, with the evaluation of the resolvent with respect to B, we indirectly obtain this output of the operator B at input x2. These arguments show that with DRS, the fixed point mapping T evaluates the operators A and B at the same point when the input Z0 is a fixed point. Further arguments would establish that this same point at which A and B are evaluated at is a solution by showing that the outputs of A and B sum to 0. In general, given a fixed point encoding T, S and a fixed point Z0, shouldn't the evaluation of T examine the output of all 2 or 3 operators at the purported solution S Z0? Otherwise, how could the fact that z0 is a fixed point certify that the output of the solution mapping is indeed a solution? Now let's quickly review this lemma which we had used for Theorem 1. Let M and C, a matrix and a vector, represent fixed coefficients, and let V be a vector of variables. If there is a W such that W transpose M is C transpose, in other words, if we can represent C transpose as a linear combination of the rows of M, then the linear equalities MV equals 0 imply the linear equality C transpose V equals 0. If there is no such W, in other words, if C transpose is not a linear combination of the rows of M, then there exists an instance of the variable vector V such that MV is equal to 0 but C transpose V is not equal to 0. Another way to state this theorem is to say that the linear equalities MV equals 0 imply the linear equality C transpose V equals 0 if and only if C transpose is a linear combination of the rows of M. Now let's return to the setup of 3-op RD. Can we combine the linear equalities and the fixed point condition to show that A, B, and C are evaluated at a same single point? It turns out that we cannot. However, this by itself is not a contradiction. Just because we can't show something with one approach doesn't mean it cannot be shown. However, we have a problem. If we try to proceed to construct a counterexample based on this analysis and thereby draw a contradiction, we will run into certain difficulties. I won't explain what these difficulties are, but I've tried it and things got complicated. We need a modified approach. Instead, we assume that the input z0 furthermore satisfies these additional linear equalities, in addition to the fixed point condition z0 equals tz0. Since t, s is a fixed point encoding, the fact that z0 is a fixed point should certify that the output of the solution mapping is a solution, regardless of these additional assumptions. Now can we use the linear equalities defining t, the fixed point condition, and these additional linear equalities to show that xa1 is equal to xb1 is equal to xc1? In other words, can we use these linear equalities to establish that operators a, b, and c are evaluated at the same point? The answer is that no, we cannot. Let's see why. We add the fixed point condition to the system of linear equalities. Note that -1 gets multiplied to z0, +1 gets multiplied to tz0. Next, we perform Gaussian elimination to eliminate this non-zero. Let's denote this matrix with capital M. Let's denote this variable vector with lowercase v. And let's denote this last row of the matrix capital M with lowercase m. Finally, let's call this linear equality equation number 2. Let n be the matrix such that this system of linear equalities is equivalent to these linear equalities. More specifically, let n have these many rows and these many columns. If we do the counting, these equalities add up to n-3 in total, and that number is reflected as the number of rows in matrix n. If we do the counting, there are 2n plus 2 components in the variable vector, and that number is reflected as the number of columns in the matrix n. Furthermore, let n contain only 0, 1, and -1. Let the non-zeros only be on the columns corresponding to the x variables. So those are the columns number 3, 5, 7, 9, and up to 2n plus 1. The matrix n is not unique, and the positions of the non-zeros depend on the ordering of the resolvent evaluations. Define L to be the stacked matrix of this form, and define n tilde to be the stacked matrix of this form. Remember, M is the last row of the matrix capital M. Under this notation, 0 equals LV means the variable vector V satisfies the linear equalities 2 and the linear equalities 1. Let's try to combine the rows of the linear system of equalities 0 equals LV to establish that xa1 is equal to xb1 and that xb1 is equal to xc1. By the lemma, the linear system of equalities imply these other linear equalities if and only if we can linear combine the rows of this linear system of equalities to obtain these linear equalities. Remember, 0 equals mv, the top part of the linear system 0 equals lv, looks like this. Every row of m except the last one cannot be used in the linear combination to prove a linear equality only involving the x variables. This is because any non-zero contribution will place a non-zero component on a column corresponding to z or tz. For example, if this row were to be used in the linear combination, then a non-zero component would be introduced into this column, and no other row can cancel out that non-zero. This column corresponds to z1, a z variable, and therefore any resulting linear equality will involve the variable z1. Likewise, if this row were to be used in the linear combination, then a non-zero component would be introduced to this column, and that non-zero component cannot be cancelled out by any other row. Since this column corresponds to z2, any resulting linear equality will involve the variable z2. By this logic, these rows cannot be used in the linear combination. The last row perhaps can be used. This leaves us with the rows of this linear system to show xa1 is equal to xb1 and xb1 is equal to xc1. Remember, lowercase m is the last row of the matrix capital M. The linear equality 0 equals nv enforces these linear equalities. Again, if we do the counting, these are n minus 3 equalities. Therefore, the matrix N has codimension n minus 3 times d. The single linear equality 0 equals mv can establish xa1 is equal to xb1, or it can establish xb1 is equal to xc1, but it cannot establish both. Remember, n tilde is the matrix of this form. If 0 equals n tilde v implies both xa1 is equal to xb1 and xb1 is equal to xc1, then in total, 0 equals n tilde v enforces all the x variables to be equal. If we do the counting, these are n minus 1 equalities. So n tilde would have a codimension of n minus 1 times d. But this reduction in codimension by 2d is a contradiction. We only added m to our linear system, and m is just one row. The additional row can reduce the codimension by at most d, not 2d. To summarize our progress, we have established that 0 equals LV, which is the linear system of equalities that includes the assumption that z0 is a fixed point, fails to imply both linear equalities xa1 equals xb1 and xb1 is equal to xc1. This by itself is not a contradiction. We now construct a counterexample, maximal monotone operators a, b, and c, such that t, s fails to be a fixed point in coding. Assume the dimension d is equal to 1. When d is bigger than 1, we can simply copy the following counterexample d times and use it as a counterexample for the higher dimensional space. By the lemma, there is a specific instance of the variable vector v, which we call v prime, such that 0 is equal to lv prime, but x prime a1 is not equal to x prime b1, or x prime b1 is not equal to x prime c1, or both. Without loss of generality, let's say this is true. In other words, let's say operators b and c are not evaluated at the same point. Let's define operator A so that the output of the resolvent evaluations with respect to A all come out to be xa1 prime. In particular, we achieve this by defining A to be set valued at the input ax1 prime, with the output set being this interval. For the moment, let's leave A unspecified for the other inputs. Likewise, define operator B to be set valued at the input xb1 prime, and likewise define operator C to be set valued at xc1 prime. By construction, z0 prime is a fixed point of the fixed point mapping T, because operators A, B, and C are designed to match this instance of the variable vector, and this instance of the variable vector satisfies 0 equals LV prime, and this linear system includes the fixed point condition. The solution mapping S evaluated at this fixed point will have some output. Let's call this output x prime. Since xb1 prime is not equal to xc1 prime, x prime is not equal to xb1 prime, or x prime is not equal to xc1 prime, or both is also a possibility. Without loss of generality, let's assume x prime is equal to xc1 prime. Now we define A outside of that single point to be single valued and monotonically increasing with slope 1. Likewise, we define B outside of that single point to be monotonically increasing with slope 1. This makes operators A and B maximal monotone. By construction, A plus B evaluated at the purported solution x prime is a bounded subset of R. We have not yet specified the output of the operator C at the purported solution x prime. Depending on whether x prime is to the left or to the right of the single point at which we define C to be set valued, we can define the output of C at the purported solution to be arbitrarily small or arbitrarily large while still maintaining monotonicity of C. In either case, we make the output of C at the purported solution to be single-valued and so small or so large so that 0 is not within A plus B plus C evaluated at the purported solution x prime. We extend the definition of C to all of R to make it maximal monotone. Now we have a contradiction. We have maximal monotone operators A, B, and C such that Z0 prime is a fixed point of the fixed point mapping T, but the output of the solution mapping is not a solution. This contradicts the assumption that T, S is a fixed point encoding.